Okay, going to be doing a quick review of our midterm, going over all the problems so that you guys can just review them on your own time to prepare for the final. So, starting with the first problem gave us an equilateral triangle, all with side lengths x. Our job in part A was to express the perimeter as a function of x. Now obviously the perimeter of this is just adding up each of these side lengths. So the perimeter as a function of x is equal to 3x. Part B wanted us to express the area of this function, or the area of this triangle as a function of x. And so, for that, we need to find the area of this function. Now I'm just going to split this triangle right down the middle into two triangles to give us a little bit more space to do the algebra. It's going to be the right triangle. We know that this side length is x. Since I'm splitting that right down the middle, this side length is x over 2. And the only question now is, what's this side length? We'll call it h. Because then I know that the area of a triangle is half the base times the height, which gives me this half, and then repeat for the other half of the triangle. So I need to find the area of this. Now, we're trying to express it in terms of x. So I know that the area, just in terms of variables I've written here, is h times x over 2. Now the only question is, how can I express h in terms of x? And so for that, we just use the Pythagorean Theorem. So I know that x squared plus, or x squared, the hypotenuse squared, is equal to this side squared plus this side squared. So is equal to h squared plus, when you square that, you get x squared over 4. Or in other words, h squared, we'll keep that squared for a second, is equal to x squared minus x squared over 4. So x squared minus x squared over 4. So finding h is going to equal, I'm going to take the square root of this. Before I take the square root, really quick, combine my terms. I have 1x squared minus 1/4 x squared leaves me 3/4 x squared, or 3x squared over 4, and then the square root of that. Now, plus or minus the square root of that, but since this is a distance, it's going to be positive, so we don't need to worry about the negative case. And then, so finally, take the square root of that. Another way that we can write that is h is equal to the square root of 3 times x over 2. So, when you substitute that in for h over here, then this is going to be root 3 times x squared all over 4. Okay. So the next problem was just dealing with function composition. So, oops. Oh, I lied. The next problem has 3 parts. Part A says, it gives us that sine of x is equal to 4/5, where x is in the closed interval, pi halves to pi. And our job on this one is to find cosine of x and then tangent of x. So remember, sine of x gives me the y over the hypotenuse. So if I know sine of x is equal to 4/5, I know that we're dealing with a triangle. If this is the angle x, then this is 4 and this is 5. Sine of x gives me the y, the height, over the hypotenuse, or r. And so, using the Pythagorean Theorem, I can calculate what this bottom side is. And I know that 3 squared plus 4 squared equals 5 squared. You could also just solve for this if that's not a Pythagorean triple you're familiar with. 5 squared is equal to 4 squared plus x squared. What x satisfies this equation? And you can find out really quick, it's 3. 5 squared is 25 minus 4 squared, or minus 16, just leaves us 9. Square rooted is 3. So my side's 3. And with that, we can really easily say that, okay, so cosine of x is equal to, now this just gives us the length of x. This gives us the length of our triangle. Our quadrant gives us the sine for our cosine. So since we're in pi halves to pi, if we look on our unit circle where that's located, we're talking about pi halves is right here, pi is right here, so we're talking about in this quadrant. And notice that cosine, or the x-coordinate, is always negative over here. So this triangle would actually have to be flipped right here for the angle x that we're talking about. So it's not just 3/5, cosine is minus 3/5. And then finally, tangent of x is sine of x over cosine of x. So 4/5 divided by negative 3/5 is negative 4/3. And that's part A. Part B is something similar. B, our given is that cosine of x is equal to 5/13, and x is between negative pi halves and 0. Minus pi halves and 0. Okay, so similar thing, we got to reset up our triangle, but with 5/13, and then we need to figure out what the height's going to be. So cosine, so if this is our x, then I know cosine of x is 5/13, which means that x is 5 and our r is 13, and so we need to figure out what the height of this triangle is. Once again, I know that 5, 12, 13 is a Pythagorean triple, or in other words, 5 squared plus 12 squared equals 13 squared. 5 is a number that satisfies that. You can just set it up as a quick algebra equation and solve and get 12, by the way. It's just a common one to memorize. So now, we have cosine. Our job is to find sine and tangent. Once again, sine of x is equal to the height over r, so it's going to be 12/13. And then our only question is, what's the sign of this going to be? Is it going to be positive or negative? And for that, we need to look at what quadrant we're in. We're from negative pi halves to 0. Negative pi halves is right here, 0 is right here, so this time we're in this quadrant. And notice that sign's always negative in that quadrant, so this is negative 12/13. And then, once again, tangent of x is sine over cosine. Sine over cosine, so that's going to give us 12/5, or negative 12/5, since sine's negative 12/13. So negative 12/13 divided by 5/13, 13s go out, you get negative 12 divided by 5, or negative 12/5, minus 12/5. And so that's how you do problem number 2. Problem 3 gives us a function and asks us to find the open intervals on which the function is increasing and decreasing, and to identify any local and extreme values and state where they occur. So we're looking for local and absolute extremes and places where the function is increasing and decreasing. Our function is h of x is equal to x to the 4 minus 2x squared plus 6. Now we know that our function is increasing wherever the derivative is positive, and we know that our function is decreasing anywhere where the derivative is negative. So our first task is going to be to find h prime of x. Find the derivative of this, which is just 4x cubed minus 4x. Okay, so there's h prime of x. Now, wherever our function changes from increasing to decreasing, the slope has to be 0. I can't have a positive slope and switch to a negative slope without that slope first being 0 somewhere. And so, we need to figure out where this is equal to 0. If we just factor this, so write this one where we factored, the zeros will pop out right at us. So we'll factor 4x out of both of these. So 4x, and that leaves us with x squared minus 1, and then we know how to factor a difference of squares. So this is 4x times x minus 1 times x plus 1. Okay, so h prime of x equal to 0. Where does that happen? That is where x is equal to, notice that if you plug in 0, this whole thing is 0. If you plug in 1, this whole thing is 0. And if you plug in negative 1, this whole thing is 0. So these are the 3 places where our function has a slope of 0, a derivative equal to 0. So at these points, it's not increasing or decreasing. And in between these points and the infinities, it has to be either increasing or decreasing. So set this up on a number line. Here's our 0, here's our 1, here's our -1, and then the question is, where is this function increasing and where is it decreasing? So to see if it's decreasing to the left of -2, we know it's doing neither at -1, so I said that wrong. To see if it's increasing or decreasing over here, we need to test a point to the left of -1. We'll pick -2 and see if it has a positive or negative derivative. If we plug -2 into this, we would get a negative here, we get a negative here, and we get a negative here. 3 negatives multiplied together is a negative, and so it's decreasing here. In between -1 and 0, we got to plug in a point. We'll plug in -1/2. If we plug in -1/2, this is a negative term, this is a negative term, and this is a positive term. A negative times a negative times a positive is positive, so it's increasing on this interval. Test another point here, plug in 1/2. When we plug in 1/2 there, this is positive, this is still negative, this is positive, so the whole thing's negative, because the product of those will give us a negative number. And then finally plug in a number to the right of 1, like 2. We get a positive, a positive, a positive, which altogether is positive. Okay, so here's where it's positive and negative. The only question now, well, we'll say what intervals it's increasing and decreasing really quick. So where is it increasing? It's increasing on the intervals -1 to 0. I said to express it as open intervals. And it's increasing on the open interval 1 to infinity. And it's decreasing. Where is it decreasing? It's decreasing from -infinity to -1 and from 0 to 1. So those are the intervals on which it's decreasing. Okay, next we were supposed to find the extreme values and any local max or min. So first off, this function, notice it's an even function, and so if you plug in a really big negative number, you get a really big positive number, and if you plug in a really big positive number, you get a really big positive number. So whatever this function looks like, it's roughly going to drop to side here. It's roughly going to come down, maybe do some wacky stuff, but then go back up to infinity. So it's not going to have a local max, we know that right up, or it's not going to have an extreme max, we know that right out the door. It tends towards infinity in both directions, but it will have a local max. Well, we don't know what it looks like in between, but we'll definitely have absolute mins as well as possibly local mins. So let's test each of our 3 points and see what they are. Now we know that -1 is a min because the function was decreasing, then it started increasing. So since it was going down, then started going up, it must have bottomed out. So this is at least a local min, possibly an absolute min. This is at least a local min, possibly an absolute min. And then 0 is going to be a local max because the function was increasing and then decreasing, so it hilled out. So local max, and one of these, if not both of them, is going to be our absolute min. But they're both going to be at least local min. So we have a local max at x equal to 0, and then we'll test these 2 points to see if they give us the same value. If they give us the same value, they're both local and absolute mins. So when we plug in f of -1, that gives us a height at -1. We're going to see which of these 2 points is lower. So when we plug in -1 here, what do we get? We get the exact same thing that we get when we plug in +1. Doesn't matter what it is, since it's an even function, because all our exponents are to even numbers. So -1 and 1 spell out the same numbers. So those are actually going to be absolute max, or absolute mins. So we have local max at that, and we have absolute min at x equal ±1. Okay, so that's problem number 2. Or that was problem 3. So problem 4 now is just a bunch of function composition. So it's going to give us 3 functions and give us 2 different ways to compose those 3 functions together. So our first function is f of x equal to the square root of x plus 1, g of x equal to 1 over x plus 4, and h of x equal to 1 over x. Okay, so we're supposed to find what f composed with g composed with h of x looks like. What does this equal? And then, in the reverse order, h composed with g composed with f. So we'll do this for order first. So this is the same thing as f of g of h of x. If you go back and look up our definition for what this composition symbol means at a point x. Anyways, so now we know what h of x is. That's 1 over x. So this is f of g of h of x. So now what do we get when we plug 1 over x in for g? So we replace that x with 1 over x. So this is going to be f of, when we plug that in, we get 1 over x plus 4, which is equal to f of, get a common denominator in the denominator. So I'm going to multiply this 4, top and bottom, by x. So we have 1 over 1 plus 4x all over x. And now, 1 divided by a fraction is 1 times its reciprocal, so that just flips it. So this is equal to f of x over 1 plus 4x. Okay, now we can plug this into our function for f of x. So all that's going to do is take this, add 1 to it, put all into the radical. So this is going to be the square root of, we have x over 1 plus 4x plus 1. Now, I'm going to get a common denominator between these two terms. In other words, I'm going to take this 1 and multiply top and bottom by 1 plus 4x. So it's going to be square root of, if I multiply 1 by 1 plus 4x, it's just going to be 1 plus 4x, but then we need to add this other x, so it's going to be 1 plus 5x in the numerator. And then the denominator, we still just have 1 plus 4x. And that is our answer, I hope. Yeah, that's right. Okay, so now, next we're going to find h composed with g composed with f. We're going to do it in reverse order here. Well, just the reverse order that we did it there. We solve it an identical way. So this is still just the exact same thing as now h of g of f of x. In parentheses. Okay. So now we know what f of x is. That's the square root of x plus 1. So this is h of g of f of x. Square root x plus 1. Okay. Now when we plug that in for g, we just replace x with the square root of x plus 1. So it's going to be 1 over the square root of x plus 1, all plus 4. So we have h of 1 over the square root of x plus 1 plus 4. And then h, all h does is flips the reciprocal of whatever you give it. So finally, this whole thing is going to just equal the square root of x plus 1 plus 4. Okay, problem 5. Problem 5 was a proof using the epsilon delta definition of a limit. And so given an epsilon, you were supposed to come up with a delta that satisfies the implication. So remember, in general, when we say that the limit as, let's see, I think this book usually uses a c. So as x approaches c of f of x is equal to L, to say that the limit as x approaches c of f of x is L is logically equivalent to saying that for every epsilon greater than 0, there exists a delta greater than 0, such that if x minus c is less than delta, then f of x minus L, that distance is less than epsilon. So another way to read this is to say the limit as x approaches c of f of x is L is logically equivalent to saying that for every epsilon there exists some delta such that if x is within delta of c, then f of x is within epsilon of L. That's what we need to prove. We need to prove that for any epsilon you choose, there always exists some delta that satisfies this implication. So when we start this, so the exact problem that we're doing, so we're trying to do a proof that the limit as x approaches 3 as x approaches 3 of 2x minus 4 is equal to 2. Now, obviously, we know that this is the case. The function's continuous at that point, so we can just plug it in, and it works. But we're supposed to prove it using this definition directly. That's explicitly given in the problem. And so, we have to show out for any epsilon out there. We know nothing about it except for some positive number. There exists some delta that makes this implication true when you replace c with 3, f of x with 2x minus 4, and L with 2. So that's what we're after. So 1, let epsilon greater than 0 be given. We don't know anything about it except for epsilon some number greater than 0. Our job is to find a delta that satisfies this. 2. So we're trying to find the delta that makes this implication true, or that makes this true. What is this in terms of our problem? So then the absolute value of f of x, our f of x is 2x minus 4, minus L, our L is 2, that's what we're saying the limit is, less than epsilon. Well, we don't say less than epsilon. We'll just evaluate this expression for a second and see if we can play with it and see if we can find a delta such that this being less than delta makes this less than epsilon. So then 2x minus 4 minus 2, well, we can simplify that. That's equal to negative 4 minus 2 is minus 6, and then we can factor 2 out of the whole thing. So it's going to be 2 times x minus 3. So now our delta already pops out at us, because notice that this part of the expression in our equation is x minus 3. C is 3 for us. Oops. Run epsilon. 3. So we are trying to find a delta such that if x minus 3 is less than delta, then 2 times x minus 3, which is the same as this whole expression, is less than epsilon. So I'm going to say 3, let delta equal epsilon over 2. I said for any epsilon you give me, I can find a delta. Here's the delta I'm saying that will make this whole implication true. 4. Then, if x minus 3 is less than delta, then that gives me delta, which is also equal to, what's delta equal to? It's equal to epsilon halves. Well, then that gives me, if I multiply both sides of this inequality by 2, that gives me that 2 times, that's a 3. Keep writing. Oh, that was an epsilon. This was a 3. Should pick a problem that has 2 different symbols. Okay, sorry. So, if I multiply both sides of this inequality by 2, then I get 2 times x minus 3 is less than epsilon. And we're done. That's what we were after. We were trying to find a delta such that if x minus c is less than delta, then f of x minus L, notice that this is the same thing as f of x minus L, then the absolute value of f of x minus L is less than epsilon. We found that delta. That delta is epsilon over 2. So we're done. Okay, so our next problem was to find a limit of a function as x approaches pi and prove that the function is continuous at pi. So let's see, our function is f of x is equal to sine of x minus sine of x. Okay, so we're trying to find the limit of this as x approaches pi and prove that this function is continuous at pi. Now notice, a function is continuous at pi. Let's see, right to the side here. F well, I'll just say the first part out, but we know a function is continuous at a point if the limit as x approaches c of f of x is equal to f of c. So a function f is continuous at a point c if and only if the limit as x approaches c of f of x is equal to f of c. So if this condition holds for our function, then not only is a function continuous at c, but we also find its limit at the same time. So, I don't know, observe that the limit as x approaches pi is the understanding of our c, of f of x is equal to, well, let's see. When we plug in pi, what do we get? When we plug in pi for sine of x, then we get 0 here. So this is equal to sine of pi minus, sine of pi is just 0, which is equal to 0, which is also equal to what we get when we just plug the point in, f of pi. And so, since as x approaches pi, we get 0, which is what we get when we plug in pi for the function. We proved that the function is continuous at that point. We kind of assumed some things that we didn't make explicit. We already knew that sine of x itself was continuous. And we already knew that x by itself was continuous. We knew that a difference of continuous functions was continuous. And we knew that composition was also continuous. So we could have argued for continuity that way. Or a composition of continuous functions is continuous. Anyways. Next we find, and this one wasn't a proof or anything, so you didn't have to use the epsilon delta definition. So our next problem, problem 7, is to find a limit. Just to find a limit, we're not proving anything here. We're just trying to evaluate a limit of some given expression. So we're trying to figure out the limit as x approaches minus 3 of 2 minus the square root of x squared minus 5 all over x plus 3. And notice right out the door that we can't just plug in to solve this limit, because when we plug in negative 3 for x, we're dividing by 0, which obviously we can't do. So we need to manipulate this expression so that we can plug in that negative 3. So our whole task here is kind of to get this x plus 3 term out of the denominator. If we can somehow get an x plus 3 to show up in the numerator, then we're happy. So there's no way around it except for just to play with the expression. The way I'm going to play with the expression, I'm going to multiply it by 1. I'm going to multiply it by a special 1. Typically, we multiply by the conjugate when we have a number and a square root part. So the conjugate of the numerator is going to be 2 plus the square root of x squared minus 5. And I have to do that top and bottom because I'm just multiplying this by 1. So notice this gives me a much uglier denominator, but it gives me a prettier numerator. Because the 2 and the 2 just gives me 2 squared. The nice thing about multiplying by the conjugate is when I multiply these two terms together, I get 2 times this square root. And when I multiply these two terms together, I get 2 times negative the square root. So those cancel out. So I just need to do this term times this term, and then this term times this term in my numerator. The denominator we won't multiply out, we'll just leave it as is. So this is equal to the limit as x approaches minus 3 of multiplying it out. In the numerator we get 2. When we multiply these two terms together we get minus, maybe I'll keep parentheses here for a second to help you follow what's happening, all over, in the denominator we still have an x plus 3, and we have that times a 2 plus the square root of x squared minus 5. Now don't bother distributing all that out because our goal is to get something in the numerator to cancel out with that x plus 3, so don't distribute that through. You're going to make life harder on yourself. Okay, so now finally, let's rewrite the numerator, see how the numerator can be re-expressed. The numerator, we can do 2 minus minus 5, 2 plus 5, which is going to be 7. Am I doing this right? something. Oh, I forgot to multiply my 2's together. This is a 4. Okay, everything's making more sense. So that was multiplying these two terms together. 2 times 2 gives me the 4. 2 times that square root cancels out with 2 times that square root, and then that square root times that square root is right there. Okay, this makes more sense now. Alright, so my numerator can be rewritten as 4 minus negative 5 is going to be 9, and then I'll have minus x squared. So up here I have 9 minus x squared all over. My denominator is still just the same thing. We'll leave it like that for now. Okay, so now this is equal to the limit as x approaches minus 3 of my numerator can be rewritten as, notice that this can be rewritten as negative x squared minus 9, and then this we're used to just for the numerator, and then we know how to factor that. So this is the same thing as negative. When I factor this part, it's going to be x minus 3, x plus 3, x minus 3, x plus 3. That's my numerator, all over, and my denominator is still this whole thing. X plus 3 times 2 plus the square root of x squared minus 5. Okay, so now the x plus 3 cancels out with the x plus 3. And now we can just plug in and take the limit. Notice that was the only thing holding us up from actually just plugging in and taking the limit. So now we get, when we plug in negative 3 here, we get negative 3 minus 3 is negative 6 times negative gives me positive 6 in the numerator. All over, in the denominator we have negative 3 squared. When we plug it in, it's going to give us 9. 9 minus 5 is 4. Square root of 4 is 2. 2 plus 2 is 4. So 3 halves. Okay, so that was that problem. Next, our job is to find the slope of a function at a point, then to find the equation of the tangent line through that point. So, let's draw out our function. Try a different marker to see if it writes a little better. We have f of x is equal to x plus 2x squared, and our point is 1, 3. So if we plug in 1 to this function, we better get 3 out, which we do. Okay, so this is a point on this function. Our job is to find the tangent line through this point of this function. Now the tangent line is a line whose slope is the derivative of this function at that point, but it's a line. So first we need to find the slope of our line. So we know our line roughly, the equation of our line so far is going to be y minus y1, which is 3, is equal to m times x minus x1. So here's the equation of our line that we know so far going through this point, but it needs to be tangent to this equation, so we got to use this equation to figure out what our slope is going to be. That's not writing much better. We'll try our orange marker. Okay. So, first thing we need to do is find the derivative of this function. Wow, that is not writing anything. That's garbage. Try our green marker. So we have f prime of x. I don't think that's going to show up good on camera. Yeah, no. Okay, so that's a no-no. Try one of these. Okay. F prime of x, not sure that's much better. F prime of x then is going to equal the derivative of x is just 1 with respect to x, plus the derivative of this with respect to x is going to be 4x. So then our slope m is going to be what you get when you plug x into this thing, our x. Our x is 1, so when we plug 1 into that thing, we're going to get 5 out. So the equation of our line is going to be y minus 3 is equal to 5 times x minus 1. And then you can move the 3 over in combined terms if you want. So, well, you should make it look a little simpler. So y is equal to we're going to have our x is just going to be 5x, and we're going to have minus 5, but plus 3 is going to be minus 2. So there's the equation of our tangent line. And now we'll try this pink. 5x minus 2. Okay, so that's all there was to that problem. Okay, our next problem is just to calculate a derivative with respect to a given variable of our function. Our function is z is equal to 1 over the square root of w squared plus w. Our job is to find the derivative of this function with respect to w. So we're trying to find dz with respect to w. So just to write it one more way to make it easier for us to see how to use the chain rule, I'm going to write this as w squared plus w all to the minus 1/2. Same thing. Just don't have a good marker. Maybe this bad black is the best we can do. Okay. So then, the derivative of z with respect to w, or z prime, I'll just call it, z prime is going to be equal to, when we take the derivative of the outside, bring down the negative 1/2, so we have minus 1/2, times w squared plus w, but you add 1, or subtract 1 from the exponent, so this is to the minus 3/2, times, don't forget the derivative of the inside, chain rule. So derivative of w squared with respect to w is 2w plus 1. So now this whole thing is going to be equal to, I'll put the negative together with the numerator, and then the 2 in this go in the denominator. So maybe I'll just write my negative out front of the whole thing. So we'll do negative, and then here's where I'll write my fraction. So in the numerator we have 2w plus 1. And then in the denominator, this term is going to go into the denominator so that we can make our exponent positive again. That's going to be w squared plus w, now to the 3/2 instead of the minus 3/2. And then don't forget our 2 here, so this needs a 2 in front. Sorry, I wrote that terrible. It's 2 times this whole thing in the denominator. Forgot about the 2 myself for a sec. And then, I think you understand the answer. I guess I could just distribute this negative through in the top to get rid of all confusion. So we'll just say negative 2 w minus 1. Okay, and that also works. So there's our answer. Next function gives us a next problem gives us a function, and our job is to find the first and second derivative with respect to x of the function. So it's y equals negative x cubed minus 7 all over x. Now you could use to calculate the derivative, you could use the quotient rule, but I think it's going to be easier to split this up into 2 separate fractions. So my first fraction, when I have negative x cubed over x, that's the same thing as negative x squared. For my second fraction, it's going to be minus 7 over x. Just rewriting this. Okay, so now y prime, my first derivative of this thing is going to be the derivative of this term, and then the derivative of that term. The derivative of a difference is the difference of derivatives. So the derivative of that gives us a minus 2x. The derivative of this, remember this is also times x to the minus 1 if you want to think about it that way instead. So when you bring down the minus 1, it makes it positive, and it's going to be x to the minus 2. So we're going to have plus 7 all over x squared now. Okay, so now we need to find the derivative of that for y double prime, our second derivative. Derivative of that is just minus 2. This one, once again, we're going to bring down, let me just rewrite this one more way so that you understand what I'm saying when I talk about bringing down these exponents. Plus 7 times x to the minus 2. This and this are the same thing. So when I bring down that minus 2, that's going to leave me with a minus 14. So minus 14, and then subtract 1 is going to be x to the minus 3, or in other words, put x cubed in the denominator. So negative 2 minus 14 over x cubed is the answer. Okay, next. Once again, just gives us a function, and our only job is to find the derivative. Problem 11 now. So, if I know that r is equal to 4 minus theta cubed times sine of 2 theta. What is the derivative of r with respect to theta is what it asks for. Just making sure you don't get confused when we plug in different variables here. So the derivative of this term is just 0, so we don't need to worry about that. For this, we need to use the product rule. So the way I'm going to group my terms is I'm going to think about negative theta cubed as one term and then sine of 2 theta as the next term. So r prime is equal to the derivative of the first multiplied by the second. So the derivative of the first multiplied by the second. What's the derivative of this? Minus 3 theta squared. So the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. So the derivative of this multiplied by this, notice either way we'll have a minus sign, so I'll write the minus there. What's the derivative of sine of 2 theta? It's going to be 2 cosine of 2 theta. Cosine of 2 theta for the derivative of the outside, and then that 2 comes from our chain rule. So the derivative of the second multiplied by the first, our first is just theta cubed. So I'm actually going to write the theta cubed before that, cosine of 2 theta. So theta cubed times cosine of 2 theta. And that's our answer, I think. Looks like it. Okay, so next one. Next, it gives us a function, and our job is just to find the slope of the function at 2 separate points. And our function's a little bit more convoluted. So our job, well, here's our expression, y squared plus x squared is equal to y to the 4th minus 2x. And our job is to find the slope at the points negative 2, 1, and at the point negative 2, negative 1. So find the slope of this function at those 2 points, where we think about y is the input and x is the output, or x is the input, y is the output. So our slope is going to be dy dx, or y prime is the symbol I'll use. So to do this, we need to do implicit differentiation. So what's the derivative of y squared with respect to x? That's going to be 2y, but then times the derivative of the inside, times the derivative of y, which is going to be y prime, plus the derivative of this, we're going to get 2x, but then times the derivative of x with respect to x. So the derivative of x with respect to x is just 1, which is why we don't have to write it. So that's why you get y primes, but not x primes. What's y prime? That's the derivative of y with respect to y. What's 1? That's the derivative of x with respect to x. We don't need that one. Okay, anyways, this is equal to 4y cubed times y prime minus 2. Okay, we're solving for y prime, so we need to get all our y primes on one side, everything else on the other side. So I'll put all my y prime terms over here and the other terms over there. Actually, let's reverse that. Put my y prime terms over here, my other terms over there, but I'm going to write my y prime terms on this side. So we still have 4 times y cubed times y prime. I was writing this term. I'm going to move the 2 to the other side, so we won't write that. But now I'm going to move this over here, so minus 2y times y prime. Minus 2y times y prime is equal to, we still have our 2x, but now I move the negative 2 to the other side, so now it's going to be a plus 2. So I added 2 to both sides of this. So that's why the 2 is now on the same side as the 2x, and it's no longer on the same side as this term, and then I subtracted this from both sides, getting rid of it on the same side as the 2x and moving it over here, which I wrote that side over here now. Okay, so now factor our y prime out of this thing. So when we factor y prime out, we're going to get 4y cubed minus 2y is equal to 2x plus 2. Okay, so now y prime is going to equal this divided by this. Notice I can divide both sides by 2. I'm going to do that at the same time. So I'm going to divide both sides by 2. That's going to make that a 2, that a 1, that a 1, that a 1. And then I'm going to take this and divide it by that term. Okay, so we have x plus 1, because we divided out the 2's, over 2y cubed minus y. Okay, so now we need to, this is our slope, but this is our slope for any x and y. We need to find it for these particular x's and y. So our y prime, when we plug in the point minus 2 and 1, is equal to, let's see, we're doing negative 2 for the x and 1 for the y. So negative 2 for the x gives us negative 2 plus 1 is still minus 1, all over. When we plug in 1 for the y, we get 2 minus 1. Yeah, 2 minus 1. So 1. So it's equal to just minus 1. Okay, let's now look at y prime evaluated at negative 2, negative 1. That's equal to, our numerator is still the same since we're still plugging in the same x, so that's still just negative 1. But our denominator now, we're plugging in negative 1 for y. So this is going to be 1 times negative 2 plus 1 is going to be negative 1. So it should just be 1. And that's what we get. Negative 1, 1. Okay. So our next problem, problem 13. Let's see, it gives us a circle and asks us to find the slope at a point, I think. Let me write it out. So it gives us, it says, we know that given that x squared plus y squared is equal to 25, and given that the derivative of x with respect to t is equal to 2, comma, what is, so we're looking for dy dt, when x is equal to 3 and y is equal to minus 4. Okay. So I've got this expression, and I'm going to differentiate both sides of this expression with respect to t. Now for this problem, I'm going to use y prime as the derivative of y with respect to t, not the derivative of y with respect to x. And I'm going to use x prime as the derivative of x with respect to t, not the derivative of x with respect to x. So this will also be x prime, and dy dt will also be y prime. That would be notation I use, just to help keep clean. So now take this expression and use implicit differentiation. So we're going to get 2x times the derivative of x with respect to t, which is x prime, plus 2y times y prime, is equal to the derivative of 25 with respect to t, that's just a constant, so 0. And so I want to solve for my y prime. So first thing I'm going to do is move this to the other side, so I know that minus 2 times y prime is equal to negative 2x times x prime. I can divide both sides by 2, which gets rid of my 2's. And now I'm going to divide both sides by y to solve for y prime. So y prime is equal to negative x times x prime all over y. Now we were looking for y prime, given that dx dt is equal to 2, or in other words, x prime is equal to 2. So I know that my x prime is 2, but my x is 3 and my y is negative 4. So plug in all those values. So we have negative x times x prime all over y. So negatives are going to go out. 2 cancels out, leaving just a 2. So we're going to be left with 3 halves. Okay, our next problem is going to give us a function, and our job is to identify the intervals on which it is concave up and concave down. Concave up and concave down. So our function is y is equal to x plus 2 cubed. So y is equal to x plus 2 cubed minus 1. Okay, and identify the intervals on which it's concave up and concave down. So concavity is given to us by the second derivative of y, so we need to find y prime and then y double prime. So y prime, the derivative of y with respect to x now, is equal to 3 times x plus 2 squared times the derivative of the inside, which is just 1, so we're good. And the derivative negative 1, 0, so we don't need that. Y double prime is equal to 6 times x plus 2. Okay, so there's our y double prime. We need to know where is this thing increasing and where is this thing decreasing. That tells us where it's concave up and concave down. Well, to figure that out, we just need to first off know where it's 0. Notice it's only 0 at negative 2. So then to the left of negative 2, it either has to be concave up or concave down. And to the right of negative 2, it has to be either concave up or concave down. So test the point. When we plug in negative 3, what do we get? When we plug in negative 3, we get a negative number, so it's concave down over here. And when we plug in number to the right, plug in something like 0, we get a positive, so it's concave up over here. So it's concave down on the interval negative infinity to negative 2, and it's concave up on the interval negative 2 to positive infinity. So that's how you do that one. Okay, next problem. Okay, problem 15 was the one where we were supposed to calculate. The problem told us to, it says that we need to find a soda can whose volume is 500 centimeters cubed. So I need to design a soda can that can hold 500 centimeters cubed of liquid. And I want to design the soda can in a right cylindrical shape so that it minimizes the amount of materials used, or in other words, we want to minimize the surface area. Now, since this is almost identical to a problem I already did in lecture, one of the example problems I did in section, should have written down what section this came from. Let's see, it would have been in chapter 4. Probably one of the later sections in chapter 4, so probably like 4.5, 4.6. I already did this exact problem, so I'm not going to rewrite it out here. You can go back to the lecture and watch me explain how to get the answer there. Because it's almost an identical problem. We just changed it here to 500 cubic centimeters instead of a full liter, which is 1,000 cubic centimeters. So, hardly changing anything. So, you can go, we already have an answer to that one recorded that you can find. Next one is to use Newton's method to get a decimal approximation of the square root of 11. So we're trying to approximate the square root of 11 using Newton's method, and I give you a hint to use the equation. Well, I tell you to use the equation. F of x is equal to x squared minus 11. Notice that a root to this is the square root of 11. Something that makes this equal to 0 also would be the square root of 11. The square root of 11 is a number that makes that equal to 0. So a root of that equation. So I said, use Newton's method starting with this and starting with x naught equal to 3. So we're going to guess that the square root of 11 is approximately 3. It's a terrible guess. Well, it's not terrible, but it's not great. And our job is to find, using Newton's method, what that results in x2 being as our approximation. So x of 0 equal to 3. Now Newton's method tells us that, we'll write this out here, x of our next term is equal to x of our previous term minus f of our previous term over f prime of our previous term. And so, that's what we need to find. So when we're looking for x of 1, then that's going to be equal to, if we're looking for x of 1, then n is 0, so that's going to be x of 0, which is 3, minus f of 3. Let's see, what do we need to find f prime really quick. So we're starting at x naught equal to 3, I'll write that here. Really quick under here, we need to find f prime. F prime of x is equal to just 2x. Okay, so x1 is equal to 3 minus f of x3. What do we get when we plug, not x3, x naught, f of x naught, which is 3. What do we get when we plug 3 into this function? We get 9 minus 11. So we're going to get negative 2 all over Plug in 3 for f prime of x, and what do we get? 6. So this is equal to 3 plus 1/3. So 3 plus 1/3, or in other words, that's going to be 13/3. Not 13/3, 10/3. Sorry. 10/3. 9/3 is 3 plus 1 more is 10/3. Okay, so now we need to find x2. x2 is equal to, repeat, except for now we're plugging this in. So x2 is equal to x1 minus f of x1 over f prime of x1. So it's equal to x1 minus f of x1. Let's see, when we plug that in up here, we get 100 over 9 minus 11. That's just plugging 10/3 in directly into that. All over 2 times 10/3, which is going to be 20/3. Okay, so this whole thing is equal to 10 over 9. If we got a common denominator over here, 11 can be rewritten as 99 over 9. So 100 over 9 minus 99 over 9 is going to be 1 over 9. So our whole numerator here is 1 over 9. Sorry, let me write my 10/3 first so I don't forget. 10/3 and then our minus here so that we don't forget. Okay. Once again, we have 100 ninths minus 99 ninths leaves me 1/9 in the numerator. And now, if you divide by 20/3, that's the same thing as multiplying it by 3 over 20. Okay, so now this is equal to, notice that we can cancel out the 9 with the 3, leaving me 3 here. So we're going to have 10/3 minus 1/60th is what we have. 10/3 minus 1/60th. Minus 1 over 60. And now, let's get this in terms of 60ths really quick, I guess. Yeah, so multiply this thing top and bottom by 20. And so that's equal to, when you multiply top and bottom by 20, we get 200 minus 1 is 199. 199 all over 60. 199 over 60. 199 over 60. And then you were expected to use your calculator to plug in 199 over 60 back into this to see that you get something really, really close to 0. So if I take 199 over 60 and plug that in here and then subtract 11, what would I get? I would get roughly, you just plug that into your calculator, you're not expected to do that by hand to get a perfect fraction, but you should get roughly 0.000278. So notice, absurdly close to 0. So this is a really, really good approximation for the square root of 11. Square root of 11 is an irrational number, so we can't write out exactly what it is as a fraction, but this gives us a great approximation. Okay, problem 17. I already explained to you guys in class. I screwed up on how I gave that problem to you. It was a bad problem. I had a typo in my test when I wrote it, and so I actually gave you something that you don't know how to solve yet, with the exception of part A. So part A, we were just supposed to find an antiderivative. So if f of x is equal to x to the minus 4 plus 2x squared plus 3, our job was to find an antiderivative of this thing. Unantiderivative or the antiderivative? Unantiderivative. So we just need one antiderivative. So in other words, we need to integrate this and we can pick c to be anything we want. We'll pick c just to be 0. So we just need to calculate the integral of that thing, and the integral of that thing, we can just do in our head, we don't need to write it out. What's the integral of x to the minus 4? Plus 1, then divide. So that's going to be x to the minus 3 divided by minus 3. Or in other words, it's going to be 1 negative 1 over 3x cubed is another way we could write it. That's x to the minus 3, and then here's minus 1/3. So add 1, then divide. Okay, plus, add 1, we get 3, and then divide gives us 2/3. So we have 2x cubed over 3, and then plus, finally, 3x. So there's an antiderivative. Okay, so next problem. Next problem gave us a function, and then we were supposed to find the antiderivative of that function at a point given some other information. So let's see. I know that it's given to me that this black is slowly getting worse. Let's try this one. Okay, it's given to me that f prime of x is equal to 2x plus 1. My job is to find f of 3 given some information. So in part A, given that f of 0 is equal to 2, for example. So really quick, let's find the antiderivative of the sinc. So if f of x is equal to that, then f of x is going to be equal to plus 1 gives us 2 divided by just gives us x squared plus x, and then plus c. We don't know what the c is. So based off of our information in parts A, B, and C, we calculate that c, and then we can calculate f of 3. So in part A, it's given to us that f of 0, I think. F of 0 is equal to 2. So if f of 0 is equal to 2, that means when we plug in 0 for f, we should get 2 out, which means our c is 2 in this case. So that's the same thing as c is equal to 2. So then, if c is equal to 2, what would I get if I plug in f of 3? F of 3 then would be equal to, we get 3 squared is 9, plus 3 is 12, plus 2 is 11, or 14. Let's say that again. 3 squared is 9, plus 3 is 12, plus 2 is 14. So we should get 14 for part A. Okay. Next, for part B, I know that f of 0, or f of 1 is equal to 0. I know that f of 1 is equal to 0. So figure out what our c is from this. So when I plug in 1 to this function, I get 1 squared plus 1 is 2. But then I know that I should get 0 for plugging in 1, so c has to be negative 2. So c is equal to negative 2. Notice that when I plug 1 into this function, I get 0. Because I get 1 squared plus 1 is all 2, minus 2 is 0. So c equals negative 2. Finally, plug f of 3 into that when I know that c is equal to negative 2. And we get 3 squared plus 3 is 12. Notice this part's always going to be 12, so it's just a question of what we do with the c. So 12, then minus 2 is going to be 10. So f of 3 is equal to 10. And then for part C, it's given to us that f of 0 is equal to 4. Well, if f of 0 is equal to 4, hopefully you can see now that c is just going to equal 4. And so f of 3 is going to equal 16. And that's part A, B, and C for that one. That was problem 18. Problem 19 was just a very straightforward integral. Just using the actual integral notation now to make sure that it didn't throw you off. So you were just supposed to find the integral of the square root of x plus 2x cubed dx, which is equal to that square root of x. You can rethink about that as x to the 1/2 if that helps you integrate it. Okay, so plus 1 and divide. So when we add 1 to that, we get 3/2. So that's going to be 2/3 x to the 3/2. Plus, when we add 1 to that, we get 4 divided by, 2's going to cancel out. We're going to get x to the 4 over 2 now instead of 4 because 2 of it was taken out by that. And then plus c for our remaining constant. And then finally, for the last problem, problem 20, you're supposed to solve the integral of minus tangent of x times secant of x dx. Now you should know from your trig tables or from when we did derivatives of trig functions that tangent of x times secant of x, that is the derivative of secant of x. It's just this negative that's throwing us off. We'll pull that negative out here, then calculate your integral. And so this is just negative secant of x plus some constant c. And that is the whole test. Obviously, if this doesn't answer all of your questions, you can ask me about more things in class, or if you just watch this on your own time and have a question about it, feel free to just text me. But that should be it. And hope this helps.